This is a video presentation of our paper Reverse Physics from Laws to Physical Assumptions. This paper was actually inspired by a comment from Christopher Hitchcock, who after a talk of mine said, "Oh, your approach reminds me of reverse mathematics, but for physics." So we thought we would actually try to formalize this a little bit. So what do we mean by reverse physics? So typically physics looks like this. Majority of things that you do in physics, you have a physical theory and then you try to devise some consequence from the physical theory and some result, effects, prediction that you go in a lab and test. Now, not all physics is this, but a lot of physics is that. In the same way, mathematics, usually you have some theorem, and from those theorems you try to develop other results, corollary calculations, some other things. And again, most of mathematics is this, not all mathematics is this. So there has been an approach in mathematical logics, in the foundations of mathematics, called reverse physics, which basically the idea is that you take theorems and you figure out what are the essential components, the axioms and the operations that are required that are needed to actually prove the theorem. So the idea is that you sort of get a different feel for how the mathematics internally works and what are pieces of mathematics sort of that belong together, that have the same expressive powers, and which are more fundamental and which aren't. So what we do in physics is something similar. We start from the physical theory and then we want to try and find what is the smallest set of physical assumptions required to rederive the theory. So the idea is that we know exactly what ingredient at a logical level, at a physical levels, are inside each of the physical theory. And so this approach, we can call it reverse physics. We start from the law and we go back to the assumptions and principles that are necessary to rederive those laws. So what I'm going to do in this talk and what we do in the paper is sort of give some examples of how this works. So we'll start by reversing classical mechanics. What does it mean? Well, we look at classical Hamiltonian mechanics and we reformulate it in 6 different ways. We'll find 6 different alternative characterizations of Hamiltonian mechanics that connect ideas from different fields. As a second example, to show how we can do dependence analysis in reverse physics, we'll look at the uncertainty principle in classical and quantum mechanics, and we'll show that the uncertainty principle is not really a consequence of the whole of the quantum theory, but just the zero entropy bound on the pure state. So that's enough to then recover the uncertainty principle in quantum mechanics and also in classical mechanics. And then we'll also look at the third law. What we'll do there is something that we call reconceptualization. What we'll find is that the zero entropy that is usually associated to a crystalline structure can be really thought as the entropy of the empty system. And this allows us to reformulate the third law of thermodynamics in a way that it's more of a logical necessity than just an empirical fact. And then we'll finish the talk with some discussion and conclusion, in general what would mean to sort of bring forward the reverse physics program. Okay, so let's start with classical mechanics. People who are familiar with my channel or the rest of my work will recognize some of the results. But let's start with standard classical Hamiltonian mechanics, standard Hamilton's equation. dq dt equals partial p of h and dp dt equal minus partial q of h. So the idea is that at every point we have a displacement field that tells us where the states are going to evolve in time. To make the math a little bit easier to follow later, what we'll do is introduce a generalized coordinate called eta, that is going to be eta 1 is going to be q and eta 2 is going to be p. And then we'll call this vector field S, which is just going to be the displacement of eta in time. And so it's just the components are going to be dq dt and dp dt. So SQ is going to be dq dt and SP is going to be dp dt. And if you look at this now as a vector field, you kind of see that there is some curl action going on there. And that should give us the first idea. Suppose that the displacement vector field S is divergenceless, which means partial q of SQ plus partial p of SP is equal to 0. Suppose we have this, then if the field is divergenceless, there exists a stream function h such that S of A is partial p of h minus partial q of h. Now, if we were in 3 dimensions, this would be a curl of a vector potential. We are not in 3 dimensions, we are in 2 dimensions, and so what we have is what is called the stream function, but it's very similar to that. And then looking at the definition of SA, of course, this component is equal to this term, this component is equal to this term, and these are just Hamilton's equations. So we can say that the divergent displacement is a necessary sufficient condition to retrieve Hamiltonian mechanics. They're equivalent way to talk about the same math. Now, another way we can look at this is by looking at how the area evolves. So if we start with a volume dq dp small q and small p, our variables in time are going to change to big Q and big P. The Jacobian is going to tell us how the area evolves. So we write the Jacobian matrix, and Q is just small q plus sq dt. So when we take the derivative, we're going to have 1 plus partial q of sq times dt. And we do all the same for all these other terms. And if you want to look at the details of the calculation, you can look at them in the paper. I'm not going to go through them right here. But the point is that once you make this multiplication, when you calculate the determinant, the Jacobian is equal to 1 plus a first order term plus the higher order terms. Now, if you notice this first order term is actually the divergence. And so when the divergence of SA is 0, this term is 0, and the Jacobian is equal to 1. So saying the Jacobian is equal to 1 said that the area is preserved is the same as saying that the divergence of S is 0. So you have yet another equivalent characterization. Okay, now these three characterizations are all about the math, about the geometry of what's happening, which is useful to have a mental picture of what's actually going on. But what does this mean physically? How do we connect to the physics? Well, to connect it to the physics, we note that statistical mechanics uses areas in phase space to count states. So if we say that the area is conserved, we're basically saying that as we evolve, the state count is conserved, which means we're mapping a certain number of states to an equal number of states. We have a one-to-one map between initial and final states. This means that we have a deterministic and reversible evolution. For each initial state, we have one and only one final state. So another characterization of the area conservation in terms of statistical mechanics is that of deterministic and reversible evolution. Now the key insight here is that the determinant of reversibility is not just a bijection. You can't just map points to points because in continuous space, counting points is not enough. So for example, if we have a dissipative system, the points are going to concentrate in smaller and smaller area around the equilibrium. And so every area will still have infinitely many points. We're mapping infinity to infinity. So if we're not looking at the size of the areas, what happens to the size of the area, we lose the fact that we might have actually a dissipative system. Mathematically, the measure that we put on discrete spaces is completely different than the measure that we put on continuous spaces. And physically, to identify discrete points, we need finitely many experiments to actually identify the point, while on a continuous we would need infinitely many experiments, we would need infinite amount of information to get them. So discrete spaces and continuous space function very differently. Now, it may be a little bit surprising that determinism and reversibility leads to the existence and conservation of energy. And the question would be, why is that? Does that make sense? Well, so let's think it like this. Suppose we have determinism and reversibility. As we define it, it means that past and future depend only on the state of the system. Knowing the state right now, I can predict the future and reconstruct the past. Now, this means that the evolution does not depend on anything else. At any point in time, I don't need to know what's happening outside of the system to be able to tell you what the system is doing. This means that the system is isolated. There is nothing in the world that is going to affect the evolution of the system. If we look at the first law of thermodynamics, a system that is isolated is a system that conserves energy. So it does make sense. So what we have recovered is really a stronger version of the first law of the thermodynamics, because it doesn't just tell us that energy is conserved. In fact, it tells us that the energy in the form of the Hamiltonian exists and it is conserved. Now, going forward, there is a link between statistical mechanics and thermodynamics through the entropy. So the entropy is Kb, the logarithm of the count of states, of the volume in phase space. Now, clearly, area conservation means entropy conservation. If we conserve W, we conserve S, which means And not only that the system is reversible in the sense I can reconstruct the previous state, but it's also reversible in the thermodynamic sense. I haven't increased entropy, I can reverse, I can go back to the original state. So we have yet another characterization, which is deterministic and thermodynamically reversible evolution. Now we looked at one type of entropy. There is another type of entropy that comes from information theory. So we have a distribution over phase space, then the information entropy is minus the integral of rho log rho in dq. How does this evolve in time? Well, if we look at the time evolution of the entropy, we find that the entropy is equal to the original entropy minus the integral of rho, the logarithm of the Jacobian determinant over the full space. But if the Jacobian determinant is 1, as we said when we have area conservation, the Jacobian determinant is 1, then the logarithm is 1 is 0, and therefore we have information conservation. So yet another characterization of Hamiltonian mechanics for 1 degree of freedom is that of information conservation in terms of the information entropy. Now, information entropy is sometimes thought as an uncertainty, so let's see if there is another characterization using uncertainty. So the best way to characterize uncertainty, again, if you have a distribution, is look at the covariance matrix. And the determinant of the covariance matrix quantifies the uncertainty in a way that, for example, is rotation invariant. So how does this change under the evolution? Well, again, the evolution of the determinant of the covariance matrix is going to be the determinant of the Jacobian times the determinant of the original covariant matrix times, again, the determinant of the Jacobian. And this is assuming that we have a very, very narrow distribution such that we can assume that the evolution is linear in the region where the peak the distribution is evolving. Now again, if we have area conservation, the Jacobian is 1, and therefore we have uncertain conservation. Note that going back, the Jacobian in principle could be also -1, but since the transformation is continuous, we can't have a negative Jacobian, so the Jacobian has to be 1 if we are conserving the uncertainty. Therefore, again, these two things are equivalent. So uncertain conservation for small peak distribution that travel around is another characterization for Hamiltonian mechanics. So you see we have 7 different connected characterization of Hamiltonian mechanics. There are the equation, the fact that we have a divergence-less displacement, the fact that we have area conservation, then the fact that we have deterministic and reversible evolution, which really means isolation, the fact that the evolution is thermodynamically reversible, so that thermodynamic entropy is conserved, the fact that we have information entropy conservation, or the uncertainty conservation for small peak distribution. All these things are equivalent. And it seems to me that having these 7 different ways of looking at things not only gives us more intuition, gives us more tool to understand the problem. I really think that understanding classical Hamiltonian mechanics means fully understanding that there are all these different ways of looking at it and that you can pass from one to the other. So this is what we call a sort of a conceptual cluster. It's a series of ideas that seems disconnected, but actually they belong together and allows us to understand the physics, the mathematics, the information theory in a much better way. Okay, so we talked about classical mechanics, thermodynamics, statistical mechanics, a bunch of different things. The last characterization was in terms of uncertainty. So let's now switch to quantum mechanics and talk a little bit about the uncertainty principle. So the uncertainty principle is just something that tells us that the product of the standard deviation of Q and P is always greater or equal to h bar over 2. So the question here, what is the origin of this uncertainty? What is the cause, meaning what explains it? What is the core feature of quantum mechanics that allows us to understand this? And before going in quantum mechanics, let's try to understand how this works, for example, in classical mechanics, and see if we can find any parallel and analogies that would allow us to get a little bit more of insight in the quantum mechanics part. So we talked about the covariance matrix, and the determinant of the covariance matrix is basically the product of the variance minus the covariance squared. And the product of the variance is just the square of the product of the standard deviation. If we rearrange the covariance on the other side, we see that the product of the variances is equal to the Jacobian plus the covariance squared, but the covariance squared is a positive number, so this number always has to be greater than the determinant of the covariance matrix. So the product of the covariance greater than the determinant of the covariance matrix. But we saw that this is a constant of motion. This does not change during motion. So this can change, but it always has to be greater or equal than this. So the uncertainty is bounded during Hamiltonian evolution. So if we have it in a graph and we imagine this as being our distribution, we can stretch it in another direction, but we're never going to make the product, which would be the area around, the squared area around, greater than the determinant of the covariant matrix, which essentially is really representing this area inside the circle. And you see that the lowest bound is when there is no correlation, right? When we already have a square and we're going to get a bigger number on the uncertainty when we're tilting. And all of this intuition actually carries forward to the quantum case. But the situation here is a little bit different than the quantum case because the bound, this bound, depends on the initial condition. We can start with a different distribution that have a different uncertainty. That uncertainty is going to be conserved by Hamiltonian evolution, but it could be bigger or smaller. It can be as small as we want. So it is related, but not quite. So the bound on quantum uncertainty is intrinsic to the nature of the quantum state. So we have to find some characterization of a quantum state that is sort of intrinsic. And since the uncertainty is somewhat related to the entropy, let's look at the von Neumann entropy. Now, the von Neumann entropy for a pure state is going to be zero no matter what pure state you have. And any mixed state is going to have an entropy that is greater than zero, greater than that of the pure state. So zero is really the lowest possible entropy. So we have an intrinsic cut on the entropy that cannot be passed in quantum mechanics. So the question is, could this bound by itself explain the uncertainty principle? So to look at that, let's look at all possible distribution, classical distribution, rho of Q and P, which we imagine to be this space over here, and we imagine to order them by minus integral of rho log rho, by the information entropy, the Gibbs entropy. So higher entropy in distribution will be here, lower entropy distribution will be here. So let's fix the entropy to a constant I0 and consider all the distribution that have that entropy. So in this region, we are going to have all distributions that have an entropy that is I0. Now, if you make the calculation, we'll find that the product of the standard deviation for those distributions is going to be greater or equal to the exponential of I0 over 2 pi e. So as we go now in entropy, the minimum uncertainty is going to increase, and if we go down, the minimum uncertainty decreases. And you will find that the equality of this relationship is actually when you have the product of two independent Gaussians. And again, if you're interested in the calculation, it's going to be on the paper. This means that if we have a lower bound on entropy, say 0, we're going to have a lower bound on the uncertainty. And the lowest possible uncertainty is going to be reached with the product of independent Gaussians, which is exactly what happens in quantum mechanics. The lowest uncertainty is reached by a Gaussian wave packet. Now note that the other direction does not work. If we put a lower bound on the uncertainty, we can still reach any possible entropy, if we can even go to minus infinity. So the lower bound of entropy is sort of the stronger, the more interesting condition than the bound on the uncertainty. And so we see that the lower bound for the information entropy, Gibbs or von Neumann, both in classical and quantum, leads to an uncertainty principle, both in classical and quantum mechanics. So we don't need the full quantum theory to derive the uncertainty principle. We only need the lower bound on entropy. And this is a much more precise condition, and we can actually understand this a little bit better. So the difference between quantum and classical mechanics is in classical mechanics, we can have distribution with arbitrary low entropy. So we can reduce the entropy and therefore the uncertainty as small as we want. But can we actually do that? Like, this is something that the theory allows, but can we actually prepare those ensembles physically? And this leads us to the third section, the section on the third law of the thermodynamics. As we saw, a lower entropy bound is built into quantum mechanics itself, but not in classical mechanics. It's not built into classical mechanics. But a lower bound of entropy is actually built in thermodynamics as well, in the third law. Third law, as specified by Lewis and Randall, says that every substance has a finite positive entropy, but at the absolute zero of temperature, the entropy may become zero, and does so become in the case of a perfect crystalline substances. So the question is, where does this lower bound come from? Again, in thermodynamics, it's just stated as, let's say, a phenomenological, as an experimental truth that we see, but we want to understand again, where does this come from? Can we go backwards a little bit more? So one of the key features of thermodynamic entropy is that it's additive for independent system. So the entropy of A and B is equal to the entropy of A plus the entropy of B, again on the assumption that these two systems are independent. So we're looking for a zero, and so what systems acts as zero under system composition? Well, it's the empty system. If I take A and compose it with the empty system, I still get A no matter what A is. So if we look at the entropy of the empty system, well, the empty system is equal to the empty system combined with itself, and the empty system is going to be independent of another empty system. S naught is equal to 2S naught, which means that it's equal to 0. So we already have a very natural zero for thermodynamics, the empty system. So now the question is, what do the empty system and a crystalline structure at zero temperature have in common? Well, the thing that they have in common is that they both have one way to be. Say the crystalline structure is at zero temperature, or that the system is not present, both fully determine the state of the system. There is the crystalline structure at zero temperature is rigid, and the empty system is not there, so we know everything there is to say about the empty system. So now the question becomes, why can't we have states with entropy less than that of an empty system? So suppose we had a system in a negative entropy state. Now the system, because entropy is associated with uncertainty and degeneracy, the system would be better specified than the empty system. So the system is better specified in that state than just saying the system is not there. But this is a contradiction, because saying the system is not there already tells us everything we can possibly want to know about the system. There is nothing else that can be added. And so the entropy of a state can never be lower than that of an empty system. So we can sort of rephrase the third law as no state can describe a system more accurately than stating that the system is not there in the first place. And I don't really know how to call this. I have this tentative name of principle of maximal description. But the point is that this statement is equivalent to the other one we quoted, to the third law. But it's more of a logical necessity than a phenomenological assumption that something we find experimentally. There is a logical reason of why we have the third law. And as such, it makes a better foundational starting point. So finding assumptions that have a flavor of stronger necessity than others is one of the goals of reverse physics. So now let's step back a little bit and talk about reverse physics more in general. Our goal is to have a holistic approach. We don't just want to take one theory, quantum mechanics, and look at that. No, we want to look at essentially all of the different theory in physics, find out what assumptions are there, doing reverse physics for all of them, understanding what are the underpinning for all, and then try to understand what are the parts that are sort of common for all of physics, so that we know what are the principles that are really foundationals for the whole field, and what are the ones that are specific for each subfield. And we want to do that in conjunction with all the other mathematical disciplines like measure theory, information theory, differential geometry, and so on, right? We want to boil everything down to the core, really the core assumption that we need to take. And so the idea is that we don't want a single fundamental point of view. We don't want to say something like, oh, everything is information and you don't have to worry about anything else, or everything is quantum mechanics and you don't have to worry about everything else. No, we want to really foster the idea that there are different points of view of the subjects, and switching hats is going to help you understand the whole better than just taking one particular view. Because the idea here is that the foundations of the different theories are not disconnected. There are some concerns that are sort of universally valid within physics. So we want to find those conceptual clusters, those ideas that sort of belong together, that span multiple areas of physics, math, and so on, so that we can have a more cohesive vision of our knowledge. Another thing that we want to do is to sort of stop looking at mathematics as being the fundamental, the foundation for physical theory. So if you look at Wikipedia, at mathematical physics, you find this diagram in which there is math as is sort of on top of everything, and from math you have this lower element mathematical physics, and you also derive the ontology from math, which I don't think philosophically make any sense, but that's what they have. And then physics is something that is sort of the ugly child of all these things. It's just an application of the beautiful mathematics. And I don't think this view actually is helpful and useful. What we really want to have is start from physical ideas that are connected with experimental verification, that we know what we're talking about and understanding which one are assumptions or not, so that we gather the physical requirements that we need. And we also come already equipped with the semantics for those requirements. We know what we're talking about. We start from the physics, and then we take those physical requirements and we encode it in math, which math is a useful way to capture physical requirements in a formal way so that we can manipulate them more precisely, more efficiently. So the idea is really to put physics at the center of physics, and we want to do this because at the end mathematics is not enough to describe the physics. The mathematical content of a theory can never tell us the full physical content, right? The same mathematical equation can be used in physics, biology, economics, and it's the same partial differential equation, but it means different things. And so the mathematics is never going to answer all questions. It's never going to tell us what is a state, what are the requirements and physically and operationally, so that we can talk about systems and their states. They're not going to tell us how the theory map to the experiments, because mathematics does not know about experiments, and is never going to tell us when one theory is appropriate in why one theory is appropriate in one context and not in another. So we have to do something more. To dig a little bit deeper on this, right? Any mathematical theory starts with axioms, right? The things that you assume to be true and from which everything derives. And you pick whatever axioms you want, and there is no sense in which you need one axiom. You can choose. You can choose to have the axiom about the parallel or not in your geometry. You could choose to have the continuous hypothesis or not in set theory. These are all choices, and they're effectively arbitrary choices. You pick them because you want to pick them. In physics, the situation is a lot more nuanced. There are different types of starting points. So, for example, you could say the system under study is isolated, right? In the description that you're doing, this is one of the conditions that you have. And we know that no system is ever perfectly isolated, so we know that this is technically false. But it's a simplifying assumption that in certain condition it's well verified, and so we take it. Or we could say the speed of light is invariant. Now, this is a much stronger statement. It's something that we take to be true, but it's an experimental fact. So we don't know whether it's true in all the contexts possibly. We say, okay, we see it that it's always verified, so we take it as a starting point. We could have another statement like that any system can be prepared or measured independently. So if I want to be able to talk about a chair, for example, I can talk about the chair because I can move the chair around and, for example, the table stays where it is. If every time that I move the chair, the tables will also move around, I wouldn't think that the chair was a single system. I would have the chair table system. So this type of assumption is a little bit different. It must be true, but it's more of a definitional property. Like I talk about a system because I can manipulate system independently. If I found something that couldn't be prepared and measured independently, I wouldn't say that that was a system. I would look for some other combination to talk about a system. And then there is something even stronger, even more necessary, such as the laws of nature are independent of our choice of coordinates. So if I study a system in Cartesian coordinates and then I change it to polar coordinates, it's not that my predictions are suddenly different and the system does something different. We need for all the predictions to be consistent, right? So if physics is objective, this must be true in a much more stronger sense than any of those. So you see, there is a degree of necessity. Some assumptions that we take are stronger than others. So if we can substitute an assumption with something more necessary, that's something that is of value to us, because we say, oh, what we thought was just a coincidence, was just an experimental fact, now becomes something that is actually, no, it has to be true. And so we gain some more knowledge and insight in the physics that we're trying to describe. And note that we don't even have a language for this. We don't have a way to say, a principle is the thing that must be true because otherwise things don't make sense, right? Because we call principle something like the invariance of the speed of light, which is an experimental fact, or we call principle the uncertainty principle, which is basically just a theorem in quantum mechanics. So we don't even have a good vocabulary for this. And I think this is a problem, and it's also a symptom that in physics we are like too focused on mathematical structure or other things to really go and look at more underlying fundamental principles and sort of elevate our discussion to the point that we really are discussing physical ideas and we understand how these physical ideas are related to each other. And so this is the type of things that we would like to explore more with reverse physics. So what is reverse physics? Reverse physics is an approach to the foundation of physics that starts from the physical laws and aims to go back to a suitable minimum number of assumptions. And we can do that for a number of different reasons. We might want to do because we want to reformulate a theory so that we can find more physical ideas instead of mathematical ideas. We can do dependency analysis so that we can know which part of the theory depends on which other parts and sort of understand the mapping of all these different ideas. Or we may want to do a reconceptualization, so we take something like the third law of thermodynamics, that it's really a phenomenological concept, and transform it in something that is more necessary as the characterization of the states of empty systems. So really the goal of reverse physics is to fully map conceptual relationships and dependencies between the different theories, between different aspects of those theories, and sort of help foster this higher level physical reasoning so that we can talk about physical idea, but still in a precise way, so that we know exactly what those things mean, both mathematically, physically, operationally, and so on. And that we can bring ideas from also different fields in a way that it's more consistent and more tight. And therefore, reverse physics by its nature is an interdisciplinary endeavor, and it can guide us also to create more general physical and mathematical models. So if somebody is interested to understand new physics, well, if we can understand what are the conceptual starting points of the theory that we have, we can know better of how to generalize those starting points once we start thinking in these higher level terms. So I thank you for your attention if you stayed here so far. And since I can't know everything about everything, if you're interested in helping me bring forward this project, and if you know of people that have done work that might be related or might be interesting to have discussions with to sort of stimulate ideas, please let me know, put it in the comment, send me an email. I'd really appreciate that. Thanks.